In this question, we are asked to find the inverse of a 3 by 3 matrix. So there's multiple ways that we could go about finding the inverse of any matrix. But for this question in particular, and probably the standard that you want to use is to use the row reduction algorithm. And so to get that started, what we generally always want to do is put this into an augmented matrix, where on the left-hand side is our matrix that we're trying to find the inverse of. And the right-hand side is just going to be actually a 3 by 3 matrix, the identity. And so what we are going to do here is perform row reductions on this thing until basically where the goal is going to be to turn this into the identity. So I'm going to bring this to I. And then once we've done that, the result is going to be that this will become the inverse. It's just kind of a nice result of this algorithm. So this just brings us kind of back to our traditional row reductions that we use to solve systems of equations. So I'm going to use this pivot 1 here to eliminate the 5 and the 2 below it. So I'm going to do row 2 plus 5 of row 1. And then I'm going to do row 3 plus 2 of row 1. And that should do the trick. And so we're just going to do those calculations. Make sure you do them on the entire row all the way across, as it's going to affect the right side of the augmented matrix as well. And then we're going to look ahead and see what we need to figure out for the next action. I don't really like that 2 being my next pivot, so I'm going to swap rows 2 and 3. All right, so next up, I am going to use the next pivot in line, which is now a 1, conveniently. And I should be able to use this one to eliminate the values above and below it by the usual move, adding and subtracting multiples. So I'm going to do that next. So I'm going to do row 1 is going to become row 1 plus row 2. And that should eliminate that second entry. And row 3, I'm going to subtract 2 of row 2 to get rid of that entry. So yeah, we perform those calculations. See, we're actually pretty close to reduced row echelon form, which happens to be the identity, which is a necessity if it is an invertible matrix. Yeah. And you also probably notice this was a sort of conveniently chosen matrix, and that I didn't really get any fractions in the calculations. That may not always be the case. You could potentially get some, but I did want to avoid them to kind of ease this example. So yeah, at this point, all I need to do now is use the final pivot to get rid of the elements above. So that's going to be row 1 minus row 3 and row 2 plus row 3. And that should give me the identity. And so yeah, so that last operation, that pair of operations brought the left side to the identity. This was exactly what we were looking for. So what that tells us is that actually this thing here is going to be our inverse. So it's kind of awkward to answer this one in a formal sentence. What I'm going to do is just call this thing here A. And then what I can do is say then the 8th, the -1, the inverse is going to be the matrix that's got those 3 rows or 3 columns. So 2, -1, and 3, 3, 1, and -1, 1, 1, and -2. And it's pretty easily checked. If you do want to check, you can just go back and multiply this by A in either order, and you should end up with the identity. The nice thing is that if you do find that a lot of the elements work out to be close to the identity, but if you aren't, a lot of times you can use that to go back and maybe see where your work went off a little bit. So yeah, it is a nice feature. A lot of things with linear algebra is a lot of your work is checkable.